Welcome students. We want to discuss about double integral over general regions. So in 5.1 we discussed about double integral over rectangles. So the idea was your domain D on which your function was defined was a rectangle, right? However, consider the following problem here. Here your domain is on which the function is defined is an xy plane is given by y equals to x, which is this curve here. And the other one is y equals to x squared. Sorry, x to the power 4, which almost looks like x squared, but with a little bit of more curve. So we want to define over, this is our domain D, and we want to find out the integration of function over this domain. So essentially, if you look at this, it will be integral of, so if you write it as z equals to x plus 2y, you're looking at, to find out the volume, you're looking at zdA over region D. So how do we get to this from a rectangular domain? So for that, we have two kind of domain. So one is called vertically simple domain. We say at region R is vertically simple, or type 1 if a line segment AB, if there's a line segment AB and two functions G1, G2 such that your Y is bounded between G1 and G2 and your X comes from the interval AB. So let's look at an example here. So consider this as your domain now, D, or region D. We're not talking about domain because there's no function we have defined yet. So consider this region D. This region D is vertically simple. So we will use another name for this. So instead of calling it vertically simple or type 1, we will call it as Y first. We will make this new name, the new naming clear, the reason for doing so. But first, let's focus on the definition. So here, if you look at your region D, this is of type 1 or vertically simple or Y first region. Why is that? Because your X values are bounded between A and B. So this is where your X values are, right? And your Y values are bounded by function. So your Y changes from Y equals to G2 of X. So actually starting from G1X to G2X, right? So that's why this region is of type 1. Similarly here as well, your X is changes from, so your X is between A and B, and your Y is between, value is between G1X, which is the curve here, to G2X. Another example here is AB. Again, X is between A and B, your Y is between G1X and G2X. So such a region is called vertically simple region or type 1 region, or you can call it Y first region. Similarly, let's discuss about horizontal simple region or type 2 or X first region if the following happens. So I'll draw this. So you have your, so this is your type 2, or you can call it Y. So in this case, it will be X first So what happens in this case is the following. So in this case, your y is fixed between some values c and d, and your x basically changes from this curve, which is say x equals to h1y to x equals to h2y. So this is an example of type 2. So type 2 or x first region, or we can call it horizontally simple region. Okay. So these are the two different kind of regions over which we will learn first on how to integrate. So what is the idea? So let's evaluate the integral now. So let's find out how to evaluate integrals of f of x y over these general region. So if f is vertically simple region, that means it's of type 1, that is of type 1, or y first. Now the name y first makes sense. Uh, so if you want to integrate over this region R, then what you do is you really integrate over y first, and your y changes from g1x to g2x, and then you integrate with respect to what? With respect to, then you integrate with respect to x. So this is your type 1 region integration. So you do y first and then with x. All right, so why the expression should be the way it is here? So let's see a quick proof of that. So suppose this is your region D, this region is of type 1 or y first, or if you want to call vertically simple region. So here your x is between A and B, and your y is between G1x to G2x. So the idea will go about, so how would we approach this problem? So how do we get to this formulation here? What we'll do is the following. We will define a new function. Again, let's call this capital F of xy. So we extend this to C to D for some CD. Then we are looking at f of xy to be your original function, f of xy. So note the original function is f of xy, and you're defining a new function out of it on the rectangle. So define on AB cross CD. So it's the original function if xy belongs to region D. And it is 0 otherwise. So now this function is continuous almost everywhere except the boundary of region D, possibly. What we do is we can now use the idea of over rectangle. Let's call this as rectangle R. So rectangle f of xy dA is same as integral f of xy dA over region D. Now, why is that? Because outside this domain D, the contribution, the function is 0. So if you think in the sense of volume, the contribution of that is going to be 0, right? So these two regions, these two integrals are equal. Now, so we have our d f of xy dA. Now I will use Fubini's theorem. So by Fubini's theorem, so let's mention that Fubini's theorem So Fubini's theorem gives us the power to compute it as iterated integral. So we'll iterate it first. So we want to go now y first. Yeah, that's why we call it y first. Now the name should be clear. So we want to go y first because y is changing between G1 and G2. So we'll go from C to D, and then we have A to B, f of x, y, dA. Now note the following. In C to D, the following happens. So observe that your f of xy is essentially 0 if your y is here, right here or there, right? So if your y is either less than g1x or y is greater than g2x, is going to be 0, right? So that's one. Secondly, when I wrote the iterated integral, I should not write dA, I should write dx dy or dy dx, depending on which one is integrated first. We are integrating y first, so I should write dy dx. All right. So now, so I can write this integral c to d f of x y dy. Now note that this is a function of x, so depending on what x is, it will change. So we have, this will become g1x to g2x f of xy dy. You'll say, why is that? Well, it's a one integral of one way. So it's the integration of one variable, and recall you can break it down. So if you would like, we can basically make it a bit more elaborate. Namely, we have c to d, c to g1x plus g1x to g2x plus g2x to d. Now here your function is 0. So this is 0. This is 0. This is 0. However, this becomes small f of x, right? So this becomes g1x to g2x of f of xy dy. Now, if we plug that back in, in star, or sorry, here star, so we get what, therefore integral d of f of xy dA, which is equal to, going to be a to b. Now instead of c to d, it will be g1x to g2x of f of xy, y first and then x. And that's why this region is called, again, I'm iterating, I'm repeating that y, it's a y first. So you're integrating with respect to y first. So here we get the integral, and this region, if you look at from the hash, I'm labeling that as this integral xy dA is going to be this. So we have found out now a way to integrate our function over general region, at least when it is of type 1, aka y first, aka vertically simple region. Similarly, if we have a horizontally simple region, so how will a horizontally simple region look like? So horizontally simple region looks like this. Your x is between y1 and y2. So in that case, your integral would be f of xy dA is, first you integrate with respect to x from h1y to h2y, and then you integrate with respect to y from c to d. So this is also called horizontally simple region, or of type 2, or x first. So now that we have this idea, let's proceed on doing some examples. So let's have the following. So we want to integrate this. So evaluate this integral. So although the region is already given to me, the integral limits are already given to me, I will draw the region to indicate what region are we integrating over. So we are integrating over, so we are integrating over, so your y moves from 0, which is the x-axis, to x cube. So your y is between the curve. So how do you draw this region? You basically draw an arrow like that. So y equals to 0, which is the x-axis. So you draw arrow y equals to 0, and then we have what y equals to x cube. So how does x cube looks like? Well, at 2, it's already 8. So let's say this is 2. So 1, 1. So this is your y equals to x cube, and so 0 to, so your y changes from this curve. This is your y equals to 0, right? To y equals to x cube, and your x changes from 0 to 2, so somewhere here. So this is the region over which we are integrating. This is our D. So the idea is very straightforward. So if you are integrating with respect to y first, you shoot an arrow parallel to the direction of y-axis. So the first curve it hits is your first curve, and when it gets in, it moves out, you get a second curve. So this is the region over which we are integrating. So let's integrate this directly and see what do we get. So we have 0 to 2. What is the integration of e to the power y by x with respect to y? Is going to be e to the power y by x times 1 by x, sorry, divided by the coefficient. So coefficient is 1 by x, so you need to divide by the coefficient. So you divide by the coefficient, which is same as multiplying by dividing by 1 by x is same as multiplying by x. Again, the limits are 0 to x cube dx. So this becomes 0 to 2. When you substitute x cube, you get y x cubed by x times x minus e to the power 0 by x times 0 dx. So this becomes 0 to 2 e to the x square times x dx. Now we can do this by substitution rule. So I'll just basically multiply. So note that 0 to 2 e to the power x square x dx. So I will basically multiply by 2 and divide by 2. So derivative of this is here. So you can clearly see that this is going to be e to the power x square. Now this will become, so this will become 1 by 2 e to the power x square 0 to 2, which will give me 1 by 2 e to the power 4 minus 0 e to the power 0, which is half e to the 4 minus 1. Okay, so there is a slight amount of caution here, though, that the function inside is not continuous at what? At 0. Okay, so that is something to think about. because it's not continuous at 0 or 0. So we will need to rewrite this in terms of limits, but while computing the double integral, everything seems to work out fine. Let's look at the following problem now. Again, I will first draw the region D, because so your region D is, so again, here we have your x changes from 0 to y. So in this case, it's what? It's a type 2, or it is x first region. Okay, so it is type 2. So you see your x is changing between some h1y and h2y, and your y is between c and d. So here, if you see this problem first, you have your x is changing, so it's x first. Your x is changing from 0, so you need to draw a line. So since you're talking about change of x, you need to draw a line. You need to draw an arrow in your mind for along the direction parallel to the x-axis. So first it hits 0 to y. So 0 to y is a straight line which looks like this. So 0 to y. So this is your line 0 to y. So let's see. So first your, okay. So first your x hits 0, right? So x first hits 0, which is, what is x equals to 0? That is your y-axis. So first it will hit this curve here. And then the second it hits basically is this arrow hits y, x equals to y, which is line y equals to x. And then your x is changing from, your y is changing from 0 to say 1, 2, 2, and 3. So this is your y equals to 3. So this is the region over which you are integrating. So this is your region D. So let's do this. So this integration is going to be 0 to 3. What is integration of this with respect to x? There is no x term, so it's going to be simply y squared plus 16 square root times integration of x is dx is x, 0 to y dy. Now this limit is only for x, so we have 0 to 3 square root of y squared plus 16 times y minus 0, which is dy. Now again, we can use the integration by substitution, namely, if we have, let y squared plus 16 be u. So I'm going to integrate the indefinite integral. So in that case, we get 2y dy equals to du. So therefore, if I want to just do the, so we get dy, y dy is equal to integral of square root of u du by 2. So this is u to the power half. It's going to be u to the power half plus 1, 3 by 2 divided by 3 by 2. So divided by 3 by 2. These two and these two will cancel, plus c. So my integral I is going to be y square plus 16 1 by 3 to the power 3 by 2 from 0 to 3. That is going to be 1 by 3. So when I put 3 there, I get what? I get 9. 9 plus 16 is 25. So 25 to the power 3 by 2. When I put 0, I get 16 to the power 3 by 2. And clearly, this can be simplified. Let's simplify it. And by 3, square root of 25 is 5. So 5 cube is 125. Similar here, square root of 4 is, sorry, square root of 16 is 4. 4 cube is 64. Yeah, so this is your answer for this integral. Again, I'm drawing these regions. So I'm drawing this region in an, we don't really need to draw the region unless we have to change the limits of integration. But I'm just showing you what the region D on which you're integrating looks like. Now let's look at the following integral. So we have 0 to 2 square root of 2 square root of ln 3, y going from 2, y x going from, so x is going from y by 2 to ln 3, square root of ln 3 actually, and dy is changing then from 0 to this. So let's first draw this region. So now here my x changes, so let me draw the region. So in this case, we have x first. So you're doing x first, so you have to basically shoot an arrow in direction of parallel to x-axis. So now first it hits the line y equals to x equals to y by 2, right? So x equals to y by 2. So let me draw that line. So first it hits x equals to y by 2. So which is a line of the following form. Let me use a different color. X equals to y by 2. And then it hits the curve x equals to ln 3, right? So x equals to y by 2 to x equals to square root of ln 3. Now, what is square root of ln 3? So note that ln 3 is slightly bigger than 1, right? Because ln of 2.71, like ln e is 1, right? So this is going to be slightly bigger than 1. So just going to draw a rough graph without having to use the calculator here. So this is x equals to y by 2, and we have x equals to square root of ln 3. And then your y changes from where to where? So y changes from 0 to, now notice that this point is, so you have x equals to y by 2. So y here is actually already y equals to 2x. So y is already at this point going to be 2 square root of ln 3. Yeah. So we are essentially at this point though, right? So this is the region over which we are integrating. So now this problem is interesting because now suppose I want to integrate it. We do not know elementary antiderivative of e to the power x per dx, right? We have seen this circumstances many times and we can't take an elementary antiderivative of this. So we will change it to, so this was, change it from x first region to y first. So first of all, let's see, is it possible? So let's see, where does y changes from? So y is changes from x equals to 0 to y equals to, so y changes from y equals to 0. So you shoot an arrow in this direction. So your y first hits this one here. So y equals to 0 to then it hits this one here, which is y equals to 2x. And that you can see, so this is both type x first and type y first region as well, or type 1 and type 2 both. So therefore, I'll rewrite this integral. So I'll first go, now I'm going to integrate with respect to y first. So your y, so we still have e to the x squared inside. Now where does the y changes from 0 to what is the next one? 2x dy. And then my x changes from 0 to 0 to square root of ln 3 dx. You will say, why did you change the region? First of all, with respect to x, there was no hope. You couldn't have taken the elementary antiderivative, and so the integration by this method using antiderivative method would have fallen flat, right? Already. But now when we change with respect to y, let's see. So when you're integrating with respect to y first, we get y 0 to 2x e to the power x squared 0 to square root of ln 3 dx. So this integral becomes 0 to square root of ln 3 e to the power x squared times 2x dx. And ta-da, there is an x squared there. Well, again, we if this 2x was not there, we wouldn't have been able to integrate it. But since this x squared is there, so let x squared be u. So this implies dx 2x dx equals to du. And if I want to compute the indefinite integral, this is going to be simply e to the u du, which is e to the power u, which is going to be e to the power x squared. So this integral then becomes e to the power x squared, limits are 0 to square root of ln 3. So this is going to be e to the power square root of 2, so square root of ln 3 squared, which is this, power 0, so which is 3 minus 1, which is 2. So interchanging the region here, sorry, interchanging the from going from x first to y first, we were able to do this. Question, is it always possible to change an x first region to y first? And the answer is no. Yeah. But there are methods to go around it by dividing your region into pieces. Okay. So consider the following. Let R be the region bounded by the parabolas y equals to x squared and y equals to 8 minus x squared. So let's draw this region first. So this is how your region R looks like. Your region R is bounded by the parabolas y equals to x squared, which is this parabola here, and y equals to 8 minus x squared, which is the parabola here. So you're integrating over region, this is your region D. Now we want to integrate this. So we want to give limits to x and y. So first we need to investigate which region, kind of region it is, x first or y first, right? So, well, if you take an arrow in direction of parallel to the direction of y, you hit this curve first and then you go out this curve. So your y is really between what, x squared and 8 minus x squared. So this seems to be y first region, or according to our nomenclature, uh, uh, type 1 region. The question one should ask is it also type 2 region? So is your x changing between two functions? Let's see. So let's look at x. So I'll take an arrow in this direction. So if I shoot an arrow in this direction, so since this part is not there, it will hit this curve first and come out this curve. So for the bottom part, it is changing between this curve and this curve here. They're essentially the same curve, but if you want to write it in terms of the x, it will be x equals to plus or minus square root of y. So we'll have this is your x equals to minus square root of y, and this will be x equals to plus square root of y. And on top, it changes between different curves. So, so now, so clearly this is not x first region. So I will integrate. So let me just erase all this because the idea is I am interested to integrate it as as y first region, okay, or type 1 region. So in that case, I have my y changes from which curve to which curve. Y changes from x square. So I'm shooting an arrow in the direction of parallel to the direction of y-axis. The first curve it hits is y equals to x square. The second curve it hits is y equals to x square, x, then y first, and then 0 to. So now what is my range for x? Where does my x changes from? So I need to compute these points to find out where my x changes from. So for compute to find limits for x, compute the intersection. And now to compute the intersection, we have to basically equate these two. So we have x square equals to 8 minus x square, which gives me 2x square equals to 8. This gives me x equals to plus or minus. So 4, so square root of 4, which is 2 plus or minus 2. So it will change from, so this changes from minus 2 to 2. So integration of y is, so integration of, so when we integrate this, we have minus 2 to 2. We have, so integration of x, so dy is just y, so x times y, x goes from, so y goes from x to square dx. So it should be clear that this is a substitution for y, right? So we have this is equal to minus 2 to 2 x times 8 minus x squared minus x cubed dx. All right, so if we look at this function, so we are integrating from minus 2 to 2 now. So since you're integrating from minus 2 to 2, we are in a good situation here. Why is that? Because we are looking at, so this is an even function, so this is an odd function, odd function, odd function. So if you integrate, you will get essentially 0. So this was basically using type 1 region, right? So let's say type 1 or x first, sorry, or y first region. Now we can also have done this problem using X first region. So homework, so this is done. So break region D into two type 2 or X first region and calculate the integral. That's a very interesting exercise to do so that you have hold of both type of regions and how you can break to go from one to the other. All right, now we can solve the problem we raised. To start with, we had this problem. We wanted to compute the volume of the solid that lies below this x plus 2y minus z equals to 0. So this is this plane here. And above the xy plane, y equals to x and y equals to x to the 4. So again, first things first, we'll draw the region for which we are integrating. So we'll draw the region D, which lies in the xy plane. So this is my region D, which is first y equals to, so y equals to x. So this is my plane y equals to x, and then y equals to x to the power 4. Note that power 4 is less than equal to, like between 0 and 1, the higher powers give you lesser value. So this is how your region D will look like. And over on this, you're finding the volume of the solid given by whose roof is given by this. So we have z equals to x plus 2y. And note that this is always positive, right? In this part at least. Just because you're asked to find the volume doesn't mean that what if it is z is positive and z is negative for some part. Then you have to be more careful. But in this case, we know that this is greater than equal to 0 on D. And this is your D. So which one shall we take first? So we will basically go with y first, yeah, or x first. It would not matter really. However, if you do x first, your x will be y and then 4th root of y. That's going to be slightly, nobody likes 4th roots. So we will basically go y first. So we'll integrate it to find volume. So first of all, volume is integral over this region D of z dA. Now we are looking at as a y first or type 1 first or type 1. So first we need to compute, so y is changing from where to where, so we are doing y first. So y is changing from x to the 4 to x. Now we want to see where's my x changing from. So for that, to find limits of x, compute the intersection. So we have x equals to x to the 4. This gives me x into 1 minus x cube equals to 0. This gives me x equals to 0 or x equals to 1, right? Because cube root of 1 is 1, right? In the real plane. I mean, we are doing all over R, right? Or complex numbers may be something different, but over real numbers, cube root of 1 gives us one value, which is 1. So we have 0 to 1 of this. This is your volume V, or in other words, we have 0 to 1. Now it's time to write back what your x is. So z is x plus 2y, x to the 4, x, we have y first and then x. Now when you compute this, we have 0 to 1. With respect to y, integral of that is going to be xy plus y square, x to the 4, x dx. Now this is going to be 0 to 1, x times x minus x to the 4 plus x to the power 2 minus x to the power 8 dx. Now if we compute this, we have x squared by, so x squared, so this is x squared, so x cubed by 3 minus x to the 5 by, so it's x to the 5, so x to the power 6 by 6 plus another x cubed by 3 minus x to the 9 by 9, 0 to 1. And when we simplify this, we get 1 by 3, 2 by 3, minus 1 by 6, minus 1 by 9. So, and the answer turns out to be 7 by 18. Okay. So this is how we compute integral over. So note that this could have also been seen as type 2 region or x first region. All right, the answer would be the same. So now let's look at few properties of double integral. Namely, if you take f of xy plus g of xy dA, then this is same as taking f of xy dA plus g of xy dA. So you can break the sum as, if you want to compute the sum of two functions, so if you want to compute integral of sum of two functions, you can compute them correct differently. So note that R need not be a rectangle, right? R is a general region here. Or if you want to call it, basically, you can replace it by D. Similarly, if you have C times f of xy dA, the C can come out. Also, if you have f of xy greater than or equal to g of xy, then integral f of xy over region R is going to be greater than or equal to integral of g of xy over region R. Yeah. Now, if D is union of D1 and D2, so suppose you have region D and D is, so D is union of region, say D1 and D2. This is D1, D2. Suppose D is the union of this region, and we have D equals to D union D2, X, and they don't overlap except the boundary. So at the boundary, they have common boundary, and it can be considered as a part of both of them. Then f of xy over region D, so integral of f of xy over region D is same as integral over D1 plus integral over D2. All right, so you can break the regions into parts and compute them separately. Now, this is extremely helpful where your region is neither of type 1 and neither of type 2. So you break it into regions of type 1 and type 2s, and then you can do the computation. Yeah. Okay. Similarly, we have the following. If you integrate 1 dA, you get the area of region D. Yeah, not the volume, region, right? So because the idea is, if you have a region D like this is your region D, and if you integrate 1, so 1 is a constant function, 1 on the top like that. So you are essentially computing volume of this guy, but volume of this guy is this area times 1. So essentially you get the area. All right. Another one is the estimation. So estimation is if we take f, if we integrate throughout, integration of m dA is less than equal to integration over region D or D of f of x y dA is less than equal to integration of m dA. Now this m can come out and integration of, so in this part you can take out m, you get integration of dA, which is AD, area of domain D. Similarly on this side you get AD again. So this gives you a bound on what the integral is going to be. Now, why is this result f important to us? Consider the following integral. So estimate the value of the integral e to the power x squared plus y squared dx dy over disk with center whose origin at center at origin and the radius is half. Now you may say, well, why do we need to estimate? Why can't I find the integral? Now note that this is basically going to be, you can't compute the elementary antiderivative here, right? Because if you do with respect to x first, you will be, you can leave this y square out, but you will be integrating e to the power x square, and you can't integrate e to the power x squared with respect to x, right? We have already seen that this function does not have any elementary antiderivative. We have not seen, we have discussed it often, right? So, okay, so now we will just estimate the values of it. So how do we basically go about estimating it? So for that, notice the following. We have x square plus y square. So we are on the circle of radius half. So x square plus y square is going to be less than equal to 1 by 4, and clearly it's going to be greater than equal to 0. So these are your values of x square plus y square. And you can also see that in that case, e to the power x square plus y square values are going to be between these guys, right? So, so using property f, so using property f, so this is your region D. So area of region D, let's call this as AD, is a circle of radius 1 by 2. So we know that result pi 1 by 2 square, which is pi by 4. So this is what AD is. Yeah, we have proved this using, you would have seen this in function of one variable in MATH251 when you were doing integrals to find out areas. So we get what we get in this case now. Therefore, e to the power 0 times AD is less than equal to this integral is less than equal to e to the power 1 by 4 times AD. And now when you compute this, so this is going to be AD is so pi by 4, so this implies pi by 4 is less than equal to this integral e to the power 1 by 4 times pi by 4. So this is an estimate for your what? Estimate for your integral, right? Nevertheless, it's an estimate after all, and nevertheless, it's a meaningful estimate to have. So if you notice, e to the power 1 by 4 is basically going to be 1.2. So this is basically you have pi by 4 less than equal to this integral less than equal to 1.28 times pi by 4. Yeah, so you see it's quite a reasonable estimate. Of course, not accurate, but so it gives you a reasonable estimate for this function. So thanks.